Point your finger at the sky. Now move it slowly, straight up, past the clouds, past the stratosphere, past the satellites and the International Space Station, past the moon, past the planets, past the edge of the solar system and the Oort cloud and the heliopause. Keep going, keep pointing. Up. Now ask, what is actually in that direction? Not what is in space in the general sense. We know there are stars and galaxies and cosmic web filaments out there in every direction. The specific question is, in the direction we call up, the direction perpendicular to the flat disk of our solar system, directly overhead from our perspective, standing on the surface of the Earth. What is actually there? What objects, what structures, what cosmic architecture occupies the space that is literally above and below the plane of our solar system? Because it is not what you think. The solar system is not a sphere floating in featureless space. It has an orientation, a geometry. The planets orbit the sun in a flattened disk, the ecliptic plane, and that disk is tilted at a specific angle relative to the galaxy in which it sits. That tilt and the direction it points means that above and below our solar system are not random directions into the generic cosmic background. They are specific directions that point toward specific cosmic structures, specific voids, specific regions of the galaxy and the local universe that have their own individual histories, populations, and physical properties. When you look straight up from the solar system's perspective, perpendicular to our ecliptic plane and pointing toward what astronomers call the North Ecliptic Pole, you are looking directly toward one of the most galaxy-rich views in the entire sky. A window relatively unobscured by the dust and gas of the Milky Way's disk, through which the Virgo supercluster and the cosmic web beyond it are visible with unusual clarity. The great galaxy clusters, the filaments, the sheets of matter that define the large-scale structure of the local universe, all of them visible in that direction, because you are looking out of the plane of the galaxy rather than through it. And when you look straight down, toward the South Ecliptic Pole, you are looking in the direction of one of the deepest and most cosmologically significant surveys of the universe ever conducted. The Hubble Ultra Deep Field, the James Webb Space Telescope's deepest observations. The direction in which human beings have pushed their instruments to their absolute limits to see the farthest possible objects in the observable universe. But the story goes much deeper than that, because above and below our solar system are not just directions into space. They are directions that intersect the structure of the Milky Way in specific ways, that pass through the local interstellar medium in specific ways, that are defined by the solar system's own trajectory through the galaxy. The sun is moving. The solar system oscillates. As it travels through the galaxy, the plane of the solar system bobs up and down through the galactic disk like a boat on an ocean, and the specific position in that oscillation, how far above or below the midplane of the galaxy we currently are, determines what the local stellar environment looks like, what the cosmic ray flux is, and possibly even what drives the long period cycles in Earth's geological record. All of that is the story of what is actually above and below our solar system. It is a story about orientation and geometry and the architecture of the local universe, about the specific cosmic neighborhood we inhabit and the specific cosmic structures that define our neighborhood's boundaries, about the relationship between the scale of our solar system and the scale of the galaxy and the scale of the universe beyond. It starts with the simplest possible question. Which way is up? Chapter 1, the geometry of our situation. Why up and down matter in space. Before we can talk about what is above and below the solar system, we need to establish what those words actually mean in the context of a planetary system floating in three-dimensional space with no obvious orientation. On Earth, up and down are defined by gravity. Down is toward the center of the Earth. Up is away from it. These directions are absolute and unambiguous as long as you are on or near the Earth's surface. In space, gravity still defines a local up and down. In any sufficiently massive object's gravitational field, things fall toward the object's center, and that defines the local vertical. But when you zoom out to the scale of the solar system, when you are looking at the 8 planets and their moons, and the asteroid belt and the Kuiper belt, the concept of up and down requires a different reference. The solar system has a natural plane. The 8 planets all orbit the Sun in paths that are nearly coplanar. They all lie within a few degrees of the same flat disk, called the ecliptic plane. The ecliptic plane is defined by the Earth's orbit around the Sun, and virtually all the other planetary orbits are inclined to this plane by only a few degrees. Mercury's orbit is the most inclined, at about 7 degrees. The rest are within 3 degrees of the ecliptic. The result is that the solar system, seen from outside, looks like a flat disk with the Sun at the center and the planets orbiting within it. This disk defines a natural up and down for the solar system. Above the solar system means the direction perpendicular to the ecliptic plane, pointing toward the north ecliptic pole. The point in the sky that the ecliptic plane's north face is pointing toward. Below means the opposite direction, toward the south ecliptic pole. The north ecliptic pole is located in the constellation Draco, at right ascension 18 hours 0 minutes and declination plus 66 degrees 33 minutes. If you stood above the solar system, looking down at the ecliptic plane, you would see the Sun at the center and the planets orbiting counterclockwise. The south ecliptic pole is directly opposite, in the constellation Dorado, near the boundary with Pictor. Now there is a separate question. The solar system's ecliptic plane is oriented at a specific angle relative to the Milky Way galaxy. The galaxy also has a plane, the galactic plane, and the solar system's orbital disk is tilted at about 60 degrees to the galactic plane. This means that the north ecliptic pole, what we have defined as above the solar system based on our own orbital geometry, is also tilted 60 degrees away from the galactic north pole. This distinction matters because it gives us 2 different sets of above and below. The ecliptic up and down, defined by our own planetary orbits, points in one direction. The galactic up and down, defined by the Milky Way's disk, points in a different direction 60 degrees away. For the purposes of this video, we will work primarily with the ecliptic definition, the direction perpendicular to our planetary disk, because that is the most direct answer to the question, what is above and below our solar system? In the sense a viewer standing on Earth would intuitively mean. But we will also explore the galactic perspective, because the orientation of our solar system relative to the galaxy turns out to have profound and poorly understood consequences. There is one more orientation concept that is worth establishing before we go further. The solar system is moving through the galaxy. The sun orbits the galactic center at a speed of approximately 220 kilometers per second, taking about 225 million years to complete one orbit. This direction of motion, the direction the sun is currently heading in its galactic orbit, is called the solar apex, and it lies in the direction of the constellation Hercules. The opposite direction, where the sun is coming from, is the solar antipex, in the constellation Columba. The solar apex and antipex are neither above nor below the solar system in either of the senses we have defined. They are along the plane of the galaxy, roughly perpendicular to the galactic north-south direction. But the motion toward the solar apex creates a specific asymmetry in what the solar system encounters as it travels. The interstellar medium the sun is plowing through comes predominantly from the direction of Hercules, and the interstellar structures the solar system is heading toward are different from those it has already passed through. All of these directional concepts, ecliptic north and south, galactic north and south, solar apex and antipex, are part of the full picture of what it means to ask what is above and below our solar system. They point in different directions, and they reveal different structures. Let us now go through each direction carefully and see what is actually there. Chapter 2. Above the solar system, the North Ecliptic Pole, and what it reveals. If you orient yourself with the solar system's North Pole pointing up, looking down at the ecliptic plane, with the planets orbiting counterclockwise below you, you are looking toward the constellation Draco. That direction, straight up from the north face of the solar system's disk, is one of the most scientifically valuable viewing directions in the entire sky. And the reason it is so valuable is precisely because of what is not in the way. The galaxy is a disk. Our solar system is embedded in that disk, roughly 2/3 of the way from the galactic center to the outer edge. The disk is full of stuff: stars, gas, dust, magnetic fields, cosmic ray particles. And when you try to look through the disk to see what is beyond it, all of that stuff gets in the way. The dust in particular absorbs and scatters visible and near-infrared light, obscuring the background objects behind it. This is why the Milky Way appears as a bright band across the sky. You are looking through the high-density plane of the galaxy. But the areas of sky far from this band, near the galactic poles, appear relatively dark and clear. You are looking straight out of the disk, through a minimum of obscuring material, into the intergalactic space beyond. The North Ecliptic Pole happens to be at a high galactic latitude. It is far from the galactic plane, which means it is one of the clearer windows through the galaxy. Looking in the direction of the North Ecliptic Pole, you can see farther into the cosmos with less interference from galactic foreground material than you can in most other directions. And what do you see there? You see the Virgo cluster. The Virgo cluster is the nearest large galaxy cluster to our own local group of galaxies. The gravitationally bound collection of approximately 1.3 trillion solar masses of matter located approximately 53 million light-years from the Milky Way. It is the dominant gravitational structure in our local cosmic neighborhood, containing approximately 1,300 galaxies, including several giant elliptical galaxies, most notably M87, whose central supermassive black hole, became famous as the first black hole ever directly imaged by the Event Horizon Telescope. The Virgo cluster is not just a nearby object of astronomical interest. It is the core of a much larger structure, the Virgo supercluster, also called Laniacea's predecessor neighborhood, that extends across approximately 110 million light-years and contains more than 100 galaxy groups and clusters, including our own local group on its periphery. The entire Virgo supercluster is gravitationally bound at some level, though not all of its member groups are gravitationally bound to each other. The accelerating expansion of the universe is working to pull the more distant members apart. But even the Virgo supercluster is not the largest structure in this direction. Zooming further out, the north ecliptic pole direction passes through or near several of the most prominent features of the local cosmic web. The vast network of galaxy filaments, sheets, and voids that constitutes the large-scale structure of the universe on scales of hundreds of millions to billions of light-years. The Great Wall, or more precisely, the CFA2 Great Wall, identified in the 1989 Redshift survey of the Center for Astrophysics, is a sheet of galaxies located approximately 200 to 300 million light-years away, that stretches for at least 500 million light-years across the sky, including through the general direction of the north ecliptic pole region. The Coma supercluster, containing the rich Coma cluster of galaxies, sits along this Great Wall at a distance of approximately 330 million light-years. The Perseus-Pisces supercluster, a filament of galaxy clusters stretching for approximately 300 million light-years, runs roughly perpendicular to our line of sight in this direction. The Sloan Great Wall, identified in the 2000s from the Sloan Digital Sky Survey data and spanning approximately 1.37 billion light-years, passes through portions of the sky accessible from the north ecliptic pole direction. These structures, the Virgo cluster, the Coma supercluster, the various superclusters, and walls and filaments of the local cosmic web, are what you find when you look straight up from the north face of our solar system's disk. Not empty space, not a uniform distribution of background galaxies. A specific, structured, historically accumulated arrangement of the universe's matter that reflects the gravitational dynamics of the past 13.8 billion years. There is something else in this direction that deserves specific attention. The north ecliptic pole direction is near the direction of the cosmic microwave background dipole, the asymmetry in the CMB temperature that reflects our local motion through the universe. We are moving, as a local group, at approximately 630 kilometers per second toward a direction in the southern sky near the constellation Hydra Centaurus. This motion is driven by the combined gravitational pull of the Virgo cluster, approximately 60 kilometers per second of the total, the Great Attractor Complex in the Hydra Centaurus region, several hundred kilometers per second, and the more distant Shapley supercluster. The fact that the north ecliptic pole direction is roughly opposite to the direction of our bulk motion means that, in a very loose sense, the cosmic structure accessible above the solar system is the structure we are in some sense moving away from, the region whose gravitational influence is being overcome by the still stronger pull of the Great Attractor in the opposite direction. The practical consequence of this geometry for astronomical observation is significant. looking straight up from the solar system through the north ecliptic pole, gives you access to the nearest large galaxy cluster, to significant portions of the cosmic web's filamentary structure, and to a relatively unobscured window through which some of the most important structures in the local universe are visible. The declination range accessible from the north ecliptic pole direction has been the target of major galaxy surveys precisely because of this combination of clarity and interesting content. Chapter 3: Below the Solar System. The Deep Field Direction. Now flip the picture. Point straight down from the solar system's disk, in the direction of the south ecliptic pole, toward the constellation Dorado. And you find yourself looking at one of the most scientifically important regions of sky in all of observational astronomy. The south ecliptic pole is near the south celestial pole, the point in the sky directly above Earth's geographic south pole. The south celestial pole is in the constellation Octans, and the south ecliptic pole is nearby, in the constellation Dorado, near its border with Pictor. This is important because the best astronomical observatories for accessing this region of sky are located in the southern hemisphere, in Chile, in Hawaii for some latitudes, at the South Pole itself for radio and millimeter wave astronomy. The direction of the south ecliptic pole is, like the north ecliptic pole, at a high galactic latitude, far from the obscuring plane of the Milky Way. But it is at a different high galactic latitude, pointing in a different direction through the intergalactic space beyond our galaxy. This direction, roughly below our solar system, is the direction of the Fornax cluster. The Fornax cluster is the second richest galaxy cluster in the nearby universe after the Virgo cluster, located approximately 65 million light-years away. It is less massive than the Virgo cluster, but in some ways more scientifically accessible, because the line of sight to it passes through even less galactic foreground material. The Fornax cluster contains approximately 1,400 galaxies and is dominated by several large elliptical galaxies, including NGC 1399, which sits at the cluster's dynamical center. The Fornax cluster is itself part of a larger structure, the Fornax-Eridanus supercluster, which extends across several hundred million light-years of sky in this general direction. But what makes the below direction of our solar system most remarkable is what astronomers chose to do with it. In 1995, astronomers using the Hubble Space Telescope made a decision that, in retrospect, was one of the most consequential observational choices in the history of astronomy. They pointed Hubble at a tiny patch of apparently empty sky in the northern celestial hemisphere, the Hubble Deep Field North, and exposed it for 10 consecutive days. The resulting image, showing approximately 3,000 faint galaxies in a region of sky about 1/30th the diameter of the full moon, revolutionized our understanding of the deep universe. Then, in 1998, they did the same thing for the southern sky. The Hubble Deep Field South was pointed at a region in the constellation Tucana, at a position relatively close to the south celestial pole and the south ecliptic pole, and therefore roughly in the direction of below our solar system. The Hubble Deep Field South confirmed that the galaxy distribution in the early universe was isotropic, that the deep universe looked the same in all directions, including both above and below the solar system. The direction near the south ecliptic pole, toward the constellation Fornax, was later chosen for the deepest survey of the sky ever attempted, the Hubble Ultra Deep Field, released in 2004. This image, taking more than 11 days of total exposure time accumulated over 400 Hubble orbits, detected approximately 10,000 galaxies in a region of sky covering about 1/12 the area of the full moon. Several of the galaxies detected in the Hubble Ultra Deep Field have since been confirmed as among the most distant objects ever observed. Galaxies at redshifts above 7, existing when the universe was less than 1 billion years old. The choice of the Hubble Ultra Deep Field location and its subsequent upgrade to the Hubble Extreme Deep Field and even deeper JWST observations was based on its low galactic foreground contamination, low zodiacal light contamination. The region is far from the ecliptic plane, so there is minimal scattered sunlight from interplanetary dust, and accessibility from the Hubble Space Telescope's orbital geometry. But the result is that the deepest view of the universe humanity has ever constructed points, in a broad sense, in the direction of below our solar system, in the direction of the south ecliptic pole, through the Fornax cluster, and into the deep universe beyond. When you look straight down from the solar system, you're not just looking at galaxies. You're looking at the most detailed map humans have ever made of the universe's history. A depth of field view that captures, in a single small patch of sky, galaxies at every cosmic epoch from the present day back to within a few 100 million years of the Big Bang. The direction below our solar system is, in the most literal sense, the direction of our deepest scientific understanding of the cosmos. But there is something else in this direction that is closer, much closer, and has a specific relationship to our solar system's local environment. In the direction of the south ecliptic pole, at a distance of only about 300 light-years from the Sun, there is a large interstellar structure called the Orion-Eridanus superbubble, or more precisely, the boundary region of it. The Orion-Eridanus superbubble is a vast cavity in the interstellar medium, blown by the stellar winds and supernova explosions from the Orion OB1 Association, a large group of hot, massive young stars located in the constellation Orion, at a distance of approximately 1,300 light-years. The bubble's southern boundary extends toward the constellation Eridanus, which sits roughly in the direction of the south ecliptic pole. The local bubble, the much smaller interstellar cavity in which our own solar system resides, may itself be connected to the Orion-Eridanus superbubble through a series of interconnected cavities in the interstellar medium. The region below our solar system is therefore not just a clear window to the deep universe. It is also the boundary of the local interstellar architecture that shapes the environment through which our solar system travels. Chapter 4. The local bubble, the cosmic cavity we call home. This is where the story gets genuinely intimate. Our solar system does not sit in a representative sample of the interstellar medium. It sits inside a bubble, a specific, large, irregular cavity in the distribution of interstellar gas and dust, approximately 300 light-years across in its longest dimension, in which the density of interstellar gas is many times lower than the galactic average. This bubble is called the local bubble, and it has been known about since the 1970s, when X-ray surveys of the sky first revealed the anomalously high temperature and anomalously low density of the interstellar medium in the solar neighborhood. The standard diffuse interstellar medium outside supernova-blown cavities has a density of roughly 1 hydrogen atom per cubic centimeter. Inside the local bubble, the density is approximately 0.001 to 0.005 atoms per cubic centimeter, 100 to 1,000 times lower than the average. The gas inside the bubble is also much hotter than typical interstellar gas, at temperatures of millions of Kelvin, compared to the thousands of Kelvin of the warm neutral medium or the tens of Kelvin of cold molecular clouds. How did the local bubble form? The consensus view, assembled from extensive modeling and observational evidence, is that it was blown by a series of supernova explosions. Between 15 and 20 individual supernova events that occurred over the past 10 to 20 million years. The progenitor stars of these supernova were members of what is now called the Scorpius-Centaurus OB Association, a group of massive young stars located in the constellations Scorpius and Centaurus that has been drifting through the galactic neighborhood over this time period. As these massive stars evolved and died in supernovae, their explosions carved out the cavity we now call the local bubble, sweeping the interstellar gas into the dense shell that forms the bubble's wall. The shell of the local bubble, the compressed interstellar gas swept up by the supernova shockwaves, is now visible as a roughly spherical structure of denser than average interstellar gas surrounding the low-density interior. Inside this shell, the Sun sits roughly centrally, not exactly at the center, but within the inner portion of the cavity, about 50 to 100 light-years from the nearest portion of the shell wall. In 2022, a paper published in Nature by Alyssa Goodman, Catherine Zucker, and their collaborators provided the most detailed three-dimensional map of the local bubble ever constructed. Using Gaia satellite distance measurements for thousands of nearby young stars, they reconstructed the shape of the local bubble's shell with unprecedented precision. Their result confirmed the bubble's irregular shape and provided a specific and surprising conclusion about the location of molecular clouds. The dense, cold clumps of gas and dust from which new stars form in the solar neighborhood. All of the molecular clouds within a few hundred light-years of the Sun are distributed on the surface of the local bubble's shell. Not inside the bubble, not randomly distributed in the local neighborhood, specifically on the shell. The dense interstellar gas swept into the wall of the bubble as the supernova shockwaves expanded has accumulated into the molecular clouds that are now forming new stars in our neighborhood, including the well-known star-forming regions in Perseus, Ophiuchus, Lupus, Chamaeleon, and Taurus that are the focus of much of the observational effort in stellar formation research. The bubble is not static, it is expanding, though slowly. The current expansion velocity of the local bubble is estimated at a few kilometers per second, much slower than the initial supernova shockwave velocities of thousands of kilometers per second. The deceleration reflects the resistance of the swept-up shell material to further expansion as the driving energy from the old supernovae dissipates. Eventually, the bubble will stop expanding and merge back into the surrounding interstellar medium. The local bubble intersects directly with the question of what is above and below our solar system. The bubble extends significantly farther in some directions than others. It is elongated rather than spherical, with its longest dimension extending roughly north-south relative to the galactic plane. This means that the solar system's line of sight perpendicular to the galactic disk, roughly the direction of galactic above and below, exits the local bubble relatively quickly and enters the surrounding interstellar medium, while the lines of sight parallel to the galactic plane remain inside the bubble for much larger distances. The boundary of the local bubble in the direction above and below the galactic plane is where the solar system transitions from its unusually empty home to the more typical interstellar environment of the galactic disk. This transition happens at distances of roughly 100 to 200 light-years from the Sun in the polar directions. Close in cosmic terms, but distant enough to contain no stars we are personally familiar with. And the solar system is moving through this bubble, not staying put in the middle, moving at its galactic orbital velocity, slowly traversing the bubble's interior on its way through the galaxy. At the Sun's current trajectory, it is estimated that we entered the local bubble approximately 2 to 3 million years ago, roughly the time of the earliest hominid evolution on Earth. And depending on the trajectory, we will exit through the bubble wall within the next few million years. What happened before we entered the local bubble? We were in the denser interstellar medium outside it. The cosmic ray flux was higher. The interstellar magnetic field was stronger. The dust density was greater. Some researchers have proposed that the transition into and out of the local bubble, which happens over cosmologically brief timescales of millions of years, may have influenced the climate history of Earth and possibly even the evolution of life through its effect on the cosmic ray flux and the solar wind's ability to shield the inner solar system from cosmic rays. This is a live area of research. The specific connections between the solar system's trajectory through the local interstellar medium and the Earth's climate record are not yet firmly established. But the question of what the solar system was moving through before it entered the bubble and what it will encounter when it exits is a real and scientifically important one. Chapter 5. The galactic oscillation, our solar system, bobs like a cork. Now we reach one of the most physically interesting aspects of what is above and below our solar system. Not just what is there, in a static sense, but how the solar system moves through the galaxy, and what that movement means for what it encounters above and below the galactic plane. The Sun is not in a fixed position within the Milky Way. It is in a circular-ish orbit around the galactic center, completing one orbit every approximately 225 million years. But this orbit is not perfectly planar. Like all stars in the galactic disk, the Sun's orbit is not confined to the exact midplane of the galaxy. Instead, it oscillates up and down through the galactic disk, like a cork bobbing on the surface of a very slowly oscillating ocean. The galactic midplane is not the same as the ecliptic midplane. The galactic midplane is defined by the plane of symmetry of the Milky Way's disk, the plane through which the density of stars, gas, and dust is highest. The ecliptic plane, defined by our solar system's orientation, is tilted 60 degrees to this galactic midplane. The oscillation we are discussing is the Sun's motion perpendicular to the galactic midplane, the motion that carries it above and below the galaxy's equator. The period of this oscillation, one complete up and down cycle through the galactic disk, is approximately 64 million years. At the current epoch, the Sun is slightly above the galactic midplane by approximately 50 to 80 light-years. This means we are currently near the north side of the galaxy. We passed through the galactic midplane approximately 2 to 3 million years ago and are moving northward, in galactic terms, toward the maximum northward displacement, which the models suggest will be reached in approximately 10 to 15 million years. The amplitude of this oscillation, how far above and below the galactic midplane the Sun travels, is approximately 200 to 300 light-years. This means that the Sun oscillates in a zone that extends from about 200 to 300 light-years above the galactic midplane to 200 to 300 light-years below it. Within this zone, the density of interstellar material, the cosmic ray flux, and the structure of the local stellar environment change in systematic ways as the Sun moves from the sparse regions above and below the disk to the denser regions near the midplane. The implications of this oscillation are significant for the Earth's long-term history and potentially for its life history. Near the galactic midplane, the density of interstellar material is highest. More gas clouds, more dust, more molecular cloud complexes that the solar system could potentially pass through. The cosmic ray flux is also highest near the midplane, where the galactic magnetic field and the density of cosmic ray sources, primarily supernova remnants, are greatest. Periods when the Sun is near the galactic midplane would correspond to periods of higher cosmic ray flux in the inner solar system, potentially affecting climate and biology on Earth. Far from the midplane, at the extremes of the oscillation, 200 to 300 light-years above or below, the stellar density is lower. The interstellar medium is more diffuse, and the cosmic ray environment is different from that near the midplane. These periods might correspond to less cosmically active phases of Earth's history. Several researchers have proposed connections between the periodicity of the Sun's galactic oscillation and periodic features in Earth's geological record. The best-known proposal is the connection between the approximately 62 million year period suggested by analysis of marine fossil diversity data and the approximately 64 million year oscillation period. The idea is that the Sun's passage through the denser regions near the galactic midplane increases the cosmic ray flux, which affects the climate and biological diversity in ways that could produce a roughly periodic signal in the fossil record. This proposal is controversial. The evidence for a 62 million year periodicity in the fossil record is debated. Different researchers applying different analytical techniques to the same fossil diversity data have reached different conclusions about whether the periodicity is real or a statistical artifact. The physical mechanism connecting cosmic ray flux to biological diversity is not clearly established, and the match between the oscillation period and the proposed biological periodicity is imprecise. But the underlying physical reality that the solar system oscillates through the galactic disk on a 64 million year timescale, and that this oscillation changes the local cosmic environment in systematic ways, is not controversial. It is established astrophysics. The Sun is currently slightly above the galactic midplane, meaning that we are in a relatively low-density region of the galactic disk, with the densest and most active part of the disk below us, in galactic terms. the question of what is immediately above and below the solar system in the galactic sense. What interstellar structures lie within a few hundred to a few thousand light years in the direction perpendicular to the galactic disk is therefore not a static question. The answer changes on million-year timescales as the Sun completes its galactic oscillation. The specific structures above and below the solar system right now are not the same structures that were above and below it 30 million years ago, when the Sun was at maximum southward displacement from the galactic midplane. And they are not the same structures that will be above and below it 30 million years from now when it reaches maximum northward displacement. The solar system does not have a permanent cosmic neighborhood. It has a temporary one, constantly changing as it oscillates through the galactic disk and orbits the galactic center. The structures that are above and below us now are geological transients in the history of our solar system's cosmic environment. Chapter 6: The Local Interstellar Medium, Our Immediate Surroundings. Zoom in from the scale of the local bubble and the galactic oscillation to the immediate vicinity of the solar system, within a few light years in the directions above and below the ecliptic plane, and the story becomes one of the local interstellar medium, the thin but structured gas and dust that fills the space between the stars in our immediate neighborhood. The heliosphere, the bubble of charged particles and magnetic field produced by the solar wind, within which the solar system's planets reside, extends approximately 100 to 200 astronomical units from the Sun in most directions before reaching the heliopause, the boundary where the solar wind meets the interstellar medium. Voyager 1, currently the most distant human-made object, crossed the heliopause in 2012 at a distance of approximately 121 astronomical units. Voyager 2 crossed it in 2018 at approximately 119 astronomical units. Beyond the heliopause, the interstellar medium begins. In the direction perpendicular to the ecliptic plane, in the direction of above and below the solar system, the heliopause boundary is at approximately this same distance, though the exact location varies depending on the density and pressure of the local interstellar medium in each direction. The immediate interstellar medium surrounding our solar system has a specific name and a specific character. We are embedded in what is called the local interstellar cloud, also known as the local fluff, a warm, partially ionized cloud of gas approximately 30 light-years across within the local bubble. The local fluff has a density of approximately 0.1 to 0.3 hydrogen atoms per cubic centimeter. Sparse by the standards of most interstellar clouds, but denser than the hot, tenuous gas that fills most of the local bubble's interior. The local fluff is part of a larger complex called the local interstellar complex, which includes several other nearby interstellar clouds: the G cloud, the blue cloud, the apex cloud, distributed within the local bubble at distances of a few to a few tens of light years from the Sun. These clouds are moving through the local neighborhood at velocities of a few kilometers per second relative to the Sun, driven by the pressure of the hot gas in the local bubble's interior and the gravitational dynamics of the nearby stars. The relationship between the solar system and the local fluff is not permanent. The Sun entered the local fluff approximately 45,000 to 150,000 years ago, relatively recently in cosmic terms. and is expected to exit it within the next 2,000 to 10,000 years, depending on the cloud's exact geometry and the sun's trajectory through it. Before the local fluff, the sun was presumably in the even hotter, lower density plasma of the local bubble interior, with the local interstellar medium being essentially absent. After it exits the local fluff, the sun may enter another nearby cloud or return to the hot, tenuous interior. In the directions above and below the solar system, perpendicular to the ecliptic, the local fluff extends a few tens of light years before thinning into the local bubble interior. There are no stars in these directions within the range that constitutes immediate neighborhood. The nearest stars to the sun in the direction of the north ecliptic pole are at distances of several light years and include no particularly notable objects. The nearest known star in any direction is Proxima Centauri, at 4.24 light years, but Proxima Centauri is in the general direction of the constellation Centaurus, which is in the galactic plane rather than perpendicular to the ecliptic. What is above and below the solar system in the immediate interstellar neighborhood is primarily interstellar gas and dust at the density characteristic of the local fluff, and beyond it, the low-density hot plasma of the local bubble interior. No star systems, no molecular clouds, no dramatic interstellar structures, just the thin, warm, partially ionized gas of our immediate interstellar environment, extending for tens of light years in the polar directions before giving way to the boundary conditions of the local bubble. This might seem anticlimactic, but the character of this immediate environment, the specific density, temperature, and magnetic field of the gas immediately surrounding the solar system, has real consequences for the heliosphere and therefore for the conditions inside it. The pressure of the external interstellar medium shapes the heliosphere from outside. Changes in the local interstellar medium, as the sun moves from cloud to cloud or from high density to low density regions, change the size and shape of the heliosphere, which in turn affects the cosmic ray flux inside it and potentially the climate and radiation environment of the Earth. The solar system is not an island. It is a bubble inside a bubble inside a bubble. The heliosphere, inside the local fluff, inside the local bubble, inside the Milky Way's disk. Each shell has its own properties and its own influence on what happens inside the next shell in. And the boundaries of these nested structures are different in different directions. The distance to the heliosphere boundary is different in the direction of the ecliptic poles than in the direction of the ecliptic plane. The local fluff extends further in some directions than others. The local bubble has different wall distances in different directions. The geometry of our local cosmic environment is not spherically symmetric, and the specific directions of above and below are directions that happen to point towards specific features of this nested, asymmetric structure. Chapter 7. The Oort Cloud, the solar system's outermost shell. Before we cross fully into interstellar space, we need to address the outermost structure of the solar system itself, the structure that defines the boundary between inside the solar system and above or below it, in the most literal sense. The Oort cloud is a vast, approximately spherical shell of small icy bodies, cometary nuclei, planetesimals left over from the early solar system, that extends from roughly 2,000 astronomical units from the Sun to perhaps 100,000 astronomical units, or about 1.6 light years. At its outer boundary, the Oort cloud extends almost halfway to the nearest star. The objects in the Oort cloud are in very long, slow, elongated orbits around the Sun, taking millions to hundreds of millions of years to complete a single circuit. Their combined mass is estimated at several Earth masses, though the estimate is highly uncertain because no Oort cloud object has ever been directly observed in situ. They are too faint and too distant for any current instrument to detect. The Oort cloud's existence is inferred from the properties of long-period comets. Comets with orbital periods exceeding 200 years that arrive from random directions in the sky and follow extremely elongated orbits that take them from the inner solar system out to distances consistent with Oort cloud aphelion distances. These comets are believed to have been kicked out of their distant orbits by gravitational perturbations, most commonly the tidal force of the galactic disk, which varies as the solar system oscillates through the galactic plane, or the gravitational nudges of passing stars. The Oort cloud is where, above and below the solar system, starts to become meaningfully different from inside the solar system. Within the Oort cloud, objects are still gravitationally bound to the Sun. They are members of the solar system, however loosely. Beyond the Oort cloud, objects are in the free interstellar medium, not bound to our Sun at all. But the Oort cloud itself is shaped by the forces it encounters in the directions above and below the ecliptic. The galactic tidal force, the differential gravitational pull of the galaxy on the inner versus outer portions of the Oort cloud, is the primary driver of long-period comet delivery to the inner solar system. This force acts predominantly in the direction perpendicular to the galactic plane, which is roughly aligned with the directions above and below the solar system, though tilted 60 degrees from the ecliptic poles. The galactic tide compresses and stretches the Oort cloud, preferentially in the direction perpendicular to the galactic plane, pumping orbital energy into the cloud objects and sending some fraction of them onto the highly elongated orbits that become long-period comets. The galactic tidal force is therefore a real, measurable influence on what is directly above and below the solar system, mediated through the Oort cloud. The comets that arrive in the inner solar system, Halley's Comet, Comet Hale-Bopp, the spectacular comets that have brightened our skies throughout human history, are in many cases deliveries from the outer Oort cloud, perturbed into their current trajectories by the same galactic tidal force that is produced by the concentration of mass in the galactic plane below us. And above us, though in the opposite direction, in the direction of the north ecliptic pole, above the solar system, the Oort cloud extends until its objects are more influenced by the galactic tidal force and occasional stellar perturbations than by the Sun's gravity. The nearest external perturbation source in the perpendicular direction is not a specific star, but the collective gravitational field of the galactic disk, which acts as a diffuse tidal force rather than a point perturbation. In the direction of the south ecliptic pole, below the solar system, the same is true, though the specific configuration of the tidal force is mirror symmetric. The Oort cloud, then, is the physical boundary of the solar system in the above and below directions. And the forces that shape it, the galactic tide, the perturbations of passing stars, are themselves manifestations of the cosmic structures that lie above and below us. The galactic disk above and below, in the galactic sense, and the interstellar neighborhood through which we are traveling. There is one more dimension of the Oort cloud's relationship to the above and below question that is worth establishing, because it connects the immediate structure of the solar system to the very large scales we will explore in Part 2. The Oort cloud is not distributed uniformly in all directions. Its inner region, the so-called Hills cloud or inner Oort cloud, extending from roughly 2,000 to 20,000 astronomical units, is thought to be disk-like rather than spherical, with more objects in the plane of the solar system than perpendicular to it. The outer Oort cloud, from roughly 20,000 to 100,000 astronomical units, is more spherical, its originally disk-like distribution having been randomized by billions of years of gravitational perturbations from passing stars and the galactic tide. This structure means that in the directions directly above and below the ecliptic plane, the Oort cloud density transitions from the relatively sparse outer spherical component to the emptying void of interstellar space. The density of material falls as you move outward from the Sun in any direction, but the inner disk-like component provides a concentration of material near the ecliptic plane that thins out as you go perpendicular to it. This asymmetry between the ecliptic plane direction and the polar direction is a persistent theme in the solar system's structure. The solar system is flat, concentrated near its plane, and thin in the perpendicular directions, and this flatness means that the direction of above and below is consistently the direction of less material, less density, and faster transition to the surrounding interstellar environment. Chapter 8: The Galactic Poles. What is truly above and below the Milky Way? We have been working primarily with the ecliptic definition of above and below, the directions perpendicular to our planetary disk. But there is a second, and in some ways more fundamental, definition of above and below our solar system, the directions perpendicular to the Milky Way galaxy itself, the galactic poles. And the view from these directions is categorically different from the ecliptic pole view, both in what it contains and in what it means. The North Galactic Pole is located in the constellation Coma Berenices, at right ascension 12 hours 51 minutes and declination plus 27 degrees 8 minutes. The South Galactic Pole is directly opposite in the constellation Sculptor, at right ascension 0 hours 51 minutes and declination minus 27 degrees 9 minutes. These directions are the true above and below of the Milky Way's disk. The directions you would look if you wanted to see out of the galaxy perpendicular to its plane. Because these directions are 60 degrees away from the ecliptic poles we discussed in the previous chapters, they reveal different cosmic architecture. But they share the key property of the ecliptic poles. They are at high galactic latitude, far from the obscuring material in the galactic plane, providing clear windows through which the extragalactic universe is visible with minimal contamination from foreground dust and gas. The North Galactic Pole direction is among the most scientifically productive viewing directions in all of astronomy. It is the direction of the Virgo cluster. Remember that the Virgo cluster is roughly in the direction of Coma Berenices and its neighbors, which is precisely the constellation containing the North Galactic Pole. This is not a coincidence. It is a consequence of the geometry of our local cosmic neighborhood. The Virgo cluster, which is the dominant gravitational presence in the local volume, happens to lie in the direction of the North Galactic Pole, meaning that looking straight up out of the Milky Way takes you toward the nearest major galaxy cluster. The convergence of the North Galactic Pole direction with the direction toward the Virgo cluster means that the clearest window through the Milky Way points toward one of the most interesting objects in our local cosmic neighborhood. Astronomers have exploited this geometry extensively. The Virgo cluster, the Coma cluster behind it, and the large-scale filamentary structure of the local cosmic web are all accessible from the North Galactic Pole direction, with relatively little foreground absorption to cope with. But the North Galactic Pole direction does not begin with the Virgo cluster. Between us and Virgo, at much smaller distances, the North Galactic Pole window reveals the nearby universe in a way that builds toward the larger structures. The Leo group, a loose collection of galaxies, including the famous Messier galaxies, M95, M96, M105, and Leo 1 sits at roughly 35 million light-years in this general direction. The Centaurus cluster, one of the nearest rich clusters to our local group, sits at about 170 million light-years. The distribution of these intermediate distance structures traces the local cosmic web that connects our local group to the Virgo cluster and beyond. The filamentary scaffolding along which matter has been flowing for billions of years. The Coma cluster deserves specific attention in the context of the North Galactic Pole direction, because it is one of the most historically important objects in the entire history of cosmology. The Coma cluster is a rich galaxy cluster located approximately 330 million light-years away, containing over 1,000 galaxies concentrated in a region roughly 20 million light-years across. It was the observation of the Coma cluster in 1933 by the astronomer Fritz Zwicky that first revealed the existence of dark matter. Zwicky was measuring the velocities of individual galaxies within the Coma cluster, using the Doppler shifts of their spectral lines to determine how fast each galaxy was moving. From those velocities, he could estimate the total mass of the cluster needed to keep the galaxies gravitationally bound. The cluster needed enough mass to prevent the fast-moving galaxies from flying off into space. What Zwicky found was that the mass implied by the galaxy velocities was vastly larger than the mass visible in the form of stars and galaxies. By a factor of several hundred, the cluster appeared to contain far more mass than could be accounted for by its visible content. Zwicky called this missing mass Dunkel Materie, dark matter. His result was largely ignored for decades, dismissed as an error in his measurements or an artifact of the method. It was only in the 1970s when Vera Rubin and Kent Ford found the same kind of mass discrepancy in the rotation curves of individual spiral galaxies that the dark matter problem was taken seriously. And by that point, Zwicky's original Coma cluster observation, made in the direction of the North Galactic Pole, looking straight up from the Milky Way, was recognized as the first detection of the most abundant form of matter in the universe. The South Galactic Pole direction, in the constellation Sculptor, is equally historically significant and has its own catalog of important observations. The constellation Sculptor sits relatively near the South Celestial Pole, making it accessible to Southern Hemisphere observatories throughout much of the year. The sculptor group is a loose association of galaxies in this direction, at distances of roughly 10 to 15 million light-years, and one of the closest galaxy groups to the local group. The sculptor dwarf galaxy, a satellite of our own Milky Way, is in this direction. But the South Galactic Pole direction's most famous contribution to astronomy is the Hubble Deep Field South of 1998. The choice of the Hubble Deep Field South location in the constellation Tucana, adjacent to Sculptor, near both the South Galactic Pole and the South Ecliptic Pole, was partly motivated by the high galactic latitude of this region, which minimizes foreground contamination. Looking straight down from the Milky Way toward the South Galactic Pole is, in observational terms, an act of looking through the least possible interference from our own galaxy into the deep extragalactic universe. The extragalactic universe visible from the galactic poles is, in principle, the complete universe accessible to observation, not filtered through a specific local structure, not limited by a specific foreground cluster or void. Just the full statistical distribution of galaxies across cosmic history, from the nearby universe to the edge of the observable cosmos. The galactic poles are where cosmology does its most fundamental work, measuring the large-scale structure of the universe in the directions where the view is cleanest. The specific programs that have exploited this clarity are worth naming because they represent some of the most transformative observational investments in the history of astronomy. The Sloan Digital Sky Survey, which over its first 20 years imaged more than a quarter of the entire sky and measured spectra for millions of galaxies and quasars, concentrated a significant fraction of its deep imaging in the northern galactic cap, the region surrounding the North Galactic Pole. The resulting three-dimensional map of the galaxy distribution in this direction is the most detailed such map in existence, covering volumes of space reaching from tens of millions to several billion light-years. The Dark Energy Survey, operating from the Cerro Tololo Inter-American Observatory in Chile, concentrated its deep imaging on the southern galactic cap, the region surrounding the South Galactic Pole. Its 5-year survey imaged roughly 5,000 square degrees of southern sky, measuring the shapes and positions of hundreds of millions of galaxies used to study dark energy through weak gravitational lensing and large-scale structure statistics. The South Galactic Pole direction, pointing toward the Sculptor region and the South Celestial Pole, is directly above the Atacama Desert, where some of the best astronomical sites on Earth are located, making it naturally accessible to the most capable Southern Hemisphere observatories. The forthcoming Vera Rubin Observatory, currently undergoing commissioning at Cerro Pachón in Chile, will conduct the Legacy Survey of Space and Time, a 10-year program that will image the entire accessible southern sky repeatedly, building a time domain record of billions of galaxies, millions of variable stars, and potentially thousands of gravitational lensing events. The South Galactic Pole region will be observed with particularly high cadence, accumulating the deepest possible photometric data in the direction that points straight down from the Milky Way's disk and into the clearest intergalactic space accessible from Southern Hemisphere observatories. And when you look from these poles toward the extragalactic universe, what do you see structurally? You see the cosmic web, the great cosmic web of filaments and voids and clusters that constitutes the universe's large-scale organization on scales of hundreds of millions to billions of light years. You see it not concentrated in a specific direction or a specific foreground structure, but spread across the sky in the statistically representative way that an unobscured sample of the universe actually looks. The cosmic web above and below the galactic poles of the Milky Way is the universe itself, sampled fairly and clearly, giving us access to the full depth of cosmic history in the directions where our own galaxy's disk is least in the way. Chapter 9. The cosmic web in both directions, walls, voids, and the architecture of everything now, zoom out to the largest scales, hundreds of millions to billions of light years, and look at what the cosmic web looks like in the directions above and below the solar system. Both directions, north and south, ecliptic or galactic, eventually converge on the same fundamental structure when you look far enough. The hierarchical, web-like distribution of matter that defines the large-scale organization of the observable universe. The cosmic web was predicted by theoretical cosmology in the 1970s and 1980s. As researchers running the first numerical simulations of gravitational structure formation under the assumptions of lambda CDM cosmology found that matter naturally organizes into a web of filaments, sheets, and voids, the same pattern seen in observations at every scale and in every direction. The web is not random. It is the inevitable consequence of gravity amplifying the tiny initial density fluctuations of the early universe over 13.8 billion years. In the direction of the north ecliptic pole, above the solar system, the most prominent cosmic web feature at intermediate distance is the Virgo supercluster filamentary complex we have already discussed. But looking further out, the cosmic web becomes visible in its full complexity through the galaxy surveys that have mapped this region of the sky. The 2DF Galaxy Redshift Survey, the Sloan Digital Sky Survey, the 2 Mass Redshift Survey, and their successors have built three-dimensional maps of the galaxy distribution in every direction around the solar system out to billions of light years. In the north ecliptic direction, these surveys reveal the full hierarchy of cosmic structure. Galaxy groups at tens of millions of light years, clusters at hundreds of millions, superclusters and filaments at hundreds of millions to a billion, great walls and voids at billions of light years. The Perseus-Pisces supercluster is one of the most prominent filamentary structures in this direction, lying roughly perpendicular to our line of sight at a distance of approximately 200 to 250 million light years. It is one of the largest structures in the nearby universe, a filament of galaxy clusters stretching for approximately 300 million light years, containing some of the richest individual galaxy clusters known. The Perseus cluster itself, at the heart of this system, contains thousands of galaxies and is one of the brightest X-ray sources in the sky because of the hot intracluster gas filling its gravitational well. The Perseus cluster's X-ray brightness is itself scientifically significant. The hot intracluster gas, plasma at temperatures of tens of millions of Kelvin, is trapped in the gravitational well of the cluster and emits X-rays through the thermal Bremse-Strahlung process. This X-ray emission was among the first evidence discovered in the 1970s that clusters contain enormous quantities of hot gas in addition to their visible galaxies. The mass of this hot intracluster gas, which in rich clusters like Perseus exceeds the total stellar mass of all the galaxies combined, contributed to the evidence for dark matter because the pressure of the hot gas is balanced by the gravitational well of the cluster. And the total mass implied by this pressure equilibrium far exceeds what the visible stars and hot gas together account for. Looking in the north ecliptic direction, therefore, does not just show you a collection of galaxies. It shows you the sites of some of the most important discoveries in the history of cosmology, distributed along the line of sight at increasing distances. The Coma cluster, the original dark matter discovery; the Perseus cluster, the hot intracluster gas discovery; the large-scale filamentary structure of Perseus Pisces and the Great Wall, the discovery of cosmic web structure. Each of these objects is in the direction of above the solar system, and each contributed a fundamental building block of our current understanding of how matter is distributed in the universe. Beyond Perseus Pisces, in this same direction, lies a series of structures that build up the picture of the cosmic web in ever larger scales. The Pisces-Cetus supercluster complex, sometimes called the Pisces-Cetus supercluster, though it may not be gravitationally bound as a single entity, stretches across approximately 1 billion light-years in this direction, one of the largest known structures in the observable universe. It connects multiple individual superclusters, including Perseus Pisces and the Cetus supercluster, into a filamentary chain that defines the architecture of this region of the cosmic web. In the direction of the south ecliptic pole, below the solar system, the cosmic web architecture is different in its specific features, but similar in its hierarchical character. The Fornax cluster that we mentioned as the most prominent nearby feature in this direction is itself part of a larger filamentary structure, the Fornax-Eridanus supercluster, that extends southward at distances of roughly 65 to 200 million light-years. Beyond the Fornax-Eridanus complex, the south direction passes through one of the more interesting features in the nearby cosmic web, a partial void. The region at distances of roughly 150 to 300 million light-years in the southern direction contains fewer galaxies than average. A local underdensity that is part of the larger scale patterning of the cosmic web. This void is not as large or as dramatic as the famous Boötes void in the northern sky, which spans approximately 300 to 400 million light-years and is the largest known underdensity in the nearby universe. But it represents the same kind of structure, a region where matter has been gravitationally evacuated from its interior and accumulated in the surrounding filaments and sheets. There is a specific and scientifically important void structure that deserves special mention in the context of the below the solar system direction. We discussed in earlier chapters the KBC void, the large local underdensity approximately 2 billion light-years across, in which our local group is embedded. The KBC void's geometry is not perfectly symmetric. It is elongated in certain directions and has a non-uniform density profile. In the direction below the solar system, toward the south ecliptic pole, the KBC void's boundary, the transition from the void interior to the surrounding cosmic web, occurs at a specific distance that the surveys are still working to characterize precisely. What makes the void distribution in both directions above and below the solar system scientifically interesting beyond the specific. Identification of named voids is what voids collectively tell us about the physics of the universe. Voids are, in a sense, the purest expression of the universe's expansion. Regions where dark energy's accelerating expansion has overcome gravity almost completely, where the matter density has fallen so low that the local gravitational dynamics are negligible, and the Hubble expansion proceeds essentially unimpeded. In voids, the CMB photons travel through space that is as close to empty as the universe gets, experiencing almost no gravitational perturbation. This makes voids, and the direction above and below the solar system is among the best routes through void-rich territory, since you exit the galactic disk quickly and enter the intergalactic domain, among the most cosmologically pristine environments accessible to observation. The galaxy surveys that map voids in the galactic polar directions are providing some of the most precise measurements of the dark energy equation of state through the integrated Sachs-Wolf effect. The subtle temperature imprint that voids and overdensities leave on the CMB as photons pass through expanding or contracting structures on their way to our detectors. The south ecliptic direction is the direction toward the Fornax cluster and toward the Fornax-Eridanus supercluster. Whether these structures are on the near edge of the KBC void or embedded within it is a question with observational and theoretical significance for the KBC void's geometry. The ongoing deep surveys of the southern sky, the dark energy survey, the upcoming legacy survey of space and time from the Vera Rubin Observatory are providing the data needed to answer this question. But the most striking feature of the cosmic web in both directions above and below the solar system is not any specific object or cluster. It is the voids, the empty regions, the vast, nearly spherical volumes of space containing almost no galaxies, bounded by sheets and filaments of concentrated matter that make up the majority of the universe's volume. At least 80% of the universe's volume is in voids, low-density regions where the galaxy density is below the cosmic average. The filaments, sheets, and clusters that contain most of the universe's mass occupy the remaining 20% of the volume. This means that in both directions, above and below the solar system, if you shoot a ray of light, the probability that it passes through a void at some point in its journey to the edge of the observable universe is very high. The hierarchy of void sizes is itself a signature of the physics of structure formation. Small voids, a few tens of millions of light years across, are the most numerous. Large voids, hundreds of millions of light years across, are rarer but individually more dramatic in their emptiness. The Boötes void, approximately 250 to 330 million light-years across, and located roughly in the north ecliptic direction at a distance of about 700 million light-years, is the largest known void in the nearby universe. When it was discovered in 1981, its existence was so unexpected that one of its discoverers reportedly joked that if the galaxies surround the void had been sentient, they would have found the void an obvious sign that something unusual was going on. The void contains, in its interior, approximately 60 galaxies, where the cosmic average density would predict thousands. Looking above and below the solar system therefore means looking through a universe dominated by these expanses of near emptiness, punctuated by the bright concentrations of the cosmic web. The dominant visual character of the deep field images in these directions is not the galaxies themselves, but the dark background between them, the void space that constitutes the vast majority of the universe's volume, and that is most cleanly accessible in the directions that exit the galactic disk most directly. The random walk of a photon through the cosmic web is mostly a walk through emptiness, punctuated by brief passages through the denser structures of filaments and clusters. This void-dominated nature of the universe at large scales is not accidental. It is a consequence of the same gravitational dynamics that produced the cosmic web. Gravity in overdense regions attracts matter from surrounding underdense regions, emptying the voids and filling the filaments. Over time, the voids grow emptier and the filaments grow denser. The universe evolves toward greater contrast, with the cosmic web becoming more sharply defined and the voids becoming more empty as time passes. The voids above and below the solar system are windows into the structure of the universe at its most fundamental level. They are regions where the universe is, in a sense, nearly pristine, where the matter has been cleared away by gravity and the remaining low-density gas flows gently under the pressure gradient from the void interior to the surrounding denser regions. In these voids, the cosmic microwave background photons travel without significant absorption or scattering. The void interiors are, in the optical and infrared, among the most transparent regions in the observable universe, and they are most easily accessible in the directions above and below the solar system, because those are the directions that most quickly escape the material in our own galaxy's disk. Chapter 10: The Asymmetry of Our Cosmic Address. Everything we have covered so far might give the impression that above and below the solar system are mirror images, different specific objects, but the same structural character in both directions. They are not. The universe is not symmetric above and below us. Our location in the cosmic web is asymmetric, embedded in structures that extend differently in different directions, and the specific features above and below the solar system reflect that asymmetry. The fundamental asymmetry is defined by the Great Attractor. The Great Attractor is the name given to a region of space in the direction of the constellations Norma and Centaurus, at a distance of approximately 250 million light-years. It is the most powerful local gravitational attractor in our cosmic neighborhood. A massive overdensity of matter, whose gravitational influence extends across hundreds of millions of light-years, and is currently pulling our local group, the Virgo cluster, and hundreds of other nearby galaxies toward it at hundreds of kilometers per second. The Great Attractor is not in the direction of above or below the solar system in either the ecliptic or galactic sense. It is roughly in the plane of the Milky Way, in the direction where galactic foreground absorption makes it most difficult to observe. For decades, the Great Attractor remained mysterious precisely because the galactic plane obscured the view in its direction. Only with X-ray surveys, near-infrared surveys, and radio observations that could peer through the galactic dust did the true extent of the Great Attractor complex become clear. The core of the attractor is now identified with the Norma cluster, Abell 3627, an exceptionally rich galaxy cluster that sits at the convergence point of multiple large-scale filaments. The existence of the Great Attractor in one direction and not in the opposite direction creates a fundamental asymmetry in our local cosmic environment. The matter distribution is not the same in all directions from our position. Above the solar system, toward the north ecliptic pole and the Virgo cluster, the environment is moderately overdense by the cosmic average. Below, toward the south ecliptic and the Fornax cluster, it is somewhat different. But in the direction of the Great Attractor, neither above nor below but in the plane, the overdensity is dramatically higher, pulling the entire local universe in one direction. This asymmetry has specific, measurable consequences for the motion of our local group through the cosmos. We are not at rest in the universe. We are not even moving at a simple velocity relative to the cosmic expansion. We are in a complex flow, the superposition of the cosmic expansion, the gravitational pull of nearby structures, and the repulsion from nearby voids that carries us at approximately 630 kilometers per second relative to the frame defined by the cosmic microwave background. The direction of this bulk motion tells us something specific about the asymmetry above and below. Our motion has a component directed toward the Great Attractor, the dominant gravitational pull. But it also has components in other directions. The Shapley supercluster, located approximately 650 million light-years away in the direction beyond the Great Attractor, is thought to contribute an additional pull in the same general direction. The local void, the underdense region adjacent to our position in the galactic plane, repels us gravitationally. Underdensities then repel because they have less gravitational pull than the surrounding average, pushing matter towards the denser regions at their boundaries. The net result is that our solar system's trajectory through the cosmos, and therefore what will be above and below us at different points in the future, is determined by this complex gravitational landscape. The directions above and below the solar system in 1,000,000 years will not be pointing toward the same cosmic structures as they are today, not because the solar system has rotated significantly. It orbits the galaxy at a steady speed, but because the solar system has translated through the galaxy, and the galaxy has translated through the local universe. But there is a deeper asymmetry in our cosmic address that goes beyond the gravitational flow. It concerns the cosmic microwave background itself, the most perfect isotropic signal in the observable universe, which nonetheless contains small but measurable asymmetries that may reflect the structure of what is above and below us. The CMB temperature is nearly perfectly uniform across the sky, varying by only about 1 part in 100,000 from one direction to another. But within those tiny variations, there are statistical patterns that have attracted significant attention. The so-called CMB anomalies, the low quadrupole power, the alignment of the quadrupole and octupole multipoles, the hemispherical power asymmetry, are features of the CMB temperature map that appear, at some level of statistical confidence, to be aligned with specific directions in the sky. The statistical methods used to quantify these alignments are precise enough that the Planck satellite collaboration, which produced the definitive full-sky CMB map in 2018, explicitly acknowledged the anomalies in their published analysis. The Planck team found that the anomalies they had been measuring were inconsistent with a statistically isotropic Gaussian random field at the few percent level. In other words, the CMB does not look exactly the way the simplest lambda, CDM cosmological model predicts in these directions. Something is different about the large angular scale structure of the CMB in the directions aligned with the ecliptic plane, the plane of our solar system. One of the most discussed of these alignments is the so-called axis of evil, a term coined with some humor by astronomers to describe the apparent alignment of the CMB's lowest order multipoles with the ecliptic plane and with the equinoxes. The quadrupole and octopole moments of the CMB temperature map appear to be correlated with each other and with the ecliptic plane in a way that seems unlikely by chance. The probability of this alignment occurring randomly has been estimated at roughly 1 to 2%, depending on the specific analysis method. This alignment could be entirely coincidental, a statistical fluctuation in a dataset that is being analyzed in multiple ways, with the most anomalous result receiving the most attention, a form of selection bias sometimes called the look elsewhere effect. It could be a systematic artifact of the foreground subtraction process, removing the Milky Way's contribution from the CMB map, which is needed because the Milky Way is a bright foreground source that must be subtracted, might leave residuals that mimic an ecliptic alignment. Or it could be a real physical signal, a genuine asymmetry in the CMB that reflects a real asymmetry in the universe above and below the ecliptic plane. There is a fourth possibility that is rarely discussed in the mainstream literature, but is worth acknowledging. The CMB anomalies might reflect something about the topology or the geometry of the universe at scales beyond the observable horizon, a universe that is not perfectly infinite and featureless, but has some large-scale structure that produces correlated temperature patterns on opposite sides of the sky. If the universe has a preferred direction or a preferred scale at which structure changes character, that preference might be visible in the CMB anomalies as an alignment with some cosmologically preferred axis. The ecliptic alignment would then be, in this scenario, a coincidence of direction between the cosmologically preferred axis and the plane of our solar system. This is highly speculative. The current consensus is that the CMB anomalies are most likely a combination of statistical fluctuation and systematic effects. But the fact that the anomalies are aligned specifically with the ecliptic plane, the plane of our solar system, the plane that defines what we call above and below, connects the deepest cosmological measurements we can make to the most local definition of our cosmic orientation. The physical mechanisms that could produce a real CMB alignment with the ecliptic plane are limited and generally exotic. The most commonly discussed involve either a non-trivial topology of the universe, a universe that is finite and curved in ways that produce correlations between what appears above and below the ecliptic, or a large-scale asymmetry in the distribution of matter in the local universe that affects the CMB through the integrated Sachs-Wolf effect. The CMB anomalies remain unresolved. The Planck satellite confirmed their presence at high statistical confidence, but did not explain their origin. The debate about whether they are physical or systematic is ongoing, with significant and careful researchers on both sides. What is clear is that the question of what is above and below our solar system, in both the local and the cosmological sense, intersects with some of the deepest unresolved questions in cosmology. The asymmetry of our cosmic address is real in the sense that the specific gravitational environment above and below the solar system is different from the average, and different from each other. Whether it is real in the deeper sense of the CMB anomalies, reflecting genuine physical structure above and below us, that question is still open. But there is one more dimension of the asymmetry that has nothing to do with the distant universe and everything to do with our own solar system's specific history. The Sun formed approximately 4.6 billion years ago in a molecular cloud somewhere in the outer disk of the Milky Way. In the process of forming the Sun and the planetary system, the collapsing molecular cloud flattened into a rotating disk, the protoplanetary disk, whose plane became the ecliptic plane. The inclination of this disk to the galactic midplane, the 60-degree tilt that defines the relationship between the ecliptic and galactic coordinate systems, was set by the angular momentum of the specific molecular cloud parcel that collapsed to form the solar system. That specific inclination means that the ecliptic North Pole points in a specific direction relative to the galaxy, and that direction happens to be roughly toward the Virgo cluster and the richest regions of the local cosmic web. The ecliptic South Pole points roughly away from these structures, toward the Fornax cluster and the relatively emptier regions of the southern sky. This orientation was not chosen. It was the random outcome of the angular momentum of a specific molecular cloud 4.6 billion years ago. Had the Sun formed from a different parcel of the molecular cloud, one with slightly different angular momentum, the ecliptic plane would be tilted differently. The poles would point in different directions. And above and below our solar system would refer to completely different cosmic structures. This contingency, the fact that our cosmic orientation was set by an essentially random physical process in the early solar system, is philosophically interesting in a specific way. The question, what is above and below our solar system, has a specific answer, not a generic one. If you asked the same question for a solar system orbiting a star in the Andromeda Galaxy, or for one orbiting a star in the Sculptor Dwarf Galaxy, the answers would be entirely different. Different galaxy clusters in the north, different deep fields in the south, different galactic oscillation characteristics depending on the host galaxy's disk properties. Each solar system in the universe has its own specific cosmic orientation, pointing in its own specific directions, with its own specific cosmic architecture above and below. What is universal is not the answer, but the question. Not what is above and below, but the fact of having an orientation at all. Every planetary system formed from a rotating disk has a plane and therefore a pair of poles. Every such system's poles point toward specific directions in the universe that are different from any other system's poles. The universe is, in this sense, oriented differently from every location within it. The cosmic address is always local, always specific, always a product of the contingent history of one particular molecular cloud collapse billions of years ago. We live with the cosmic orientation we inherited from our formation. The specific galaxy cluster above us, the specific deep field direction below us, the specific angle at which we bob through the galactic disk, all of it was set by the initial conditions of our solar system's birth. We did not choose our cosmic address, but we are learning with increasing precision and increasing wonder exactly what that address means. Conclusion. Here is the answer to the question we started with. Point your finger straight up, perpendicular to the plane of the solar system, toward the north ecliptic pole in the constellation Draco. In that direction, at increasing distances, you pass through the local fluff, the sparse, warm plasma of the local bubble's interior, the boundary of the local bubble, where the nearest star-forming clouds are clustered on the swept-up shell of supernova-driven gas. Beyond the bubble, you enter the general interstellar medium of the Milky Way's disk, thin and structured by the magnetic field and the spiral arms. Exit the galactic disk into intergalactic space, roughly perpendicular to the plane of the Milky Way, and the Virgo cluster appears at 53 million light-years, the most massive nearby galaxy cluster, home to M87 and its famous black hole. Beyond Virgo, the Coma supercluster at 330 million light-years, the Perseus-Pisces filament, the CFA2 Great Wall, the Sloan Great Wall, and then the deep cosmic web in all its hierarchical complexity, stretching to the observable edge of the universe at 46 billion light-years. Now flip your finger straight down toward the south ecliptic pole in the constellation Dorado. In that direction, the same local journey through the local fluff and the local bubble, and then through the galactic disk and out into intergalactic space, the Fornax cluster at 65 million light-years. Beyond Fornax, the Fornax-Eridanus supercluster, and then the South Polar Deep Field, the Hubble Ultra Deep Field, and its JWST successors. Capturing the deepest view of the universe humanity has ever assembled, galaxies at redshift 14 and beyond, existing when the universe was a few 100 million years old. And all of this, the specific galaxy clusters above and below, the specific deep field locations, the specific orientation of the solar system relative to the galactic disk, was set in place 4.6 billion years ago by the angular momentum of a collapsing molecular cloud in an unremarkable corner of the Milky Way. But here is what is genuinely remarkable. We know all of this. We know the specific name and distance of the galaxy cluster above our solar system. We know the molecular basis for the star-forming clouds on the shell of the bubble we live inside. We know the period of the oscillation that bobs our solar system through the galactic disk. We know, to within a few thousand years, when we entered the local interstellar cloud we are currently moving through. We know the history of the supernovae that carved the cavity we call home. We know the redshift of the most distant galaxy in the field that points below our ecliptic plane, and we know when in cosmic history its light was emitted. We know, in other words, our cosmic address. Not just the broad strokes, not just we live in the Milky Way in a region of the universe called the local group, but the specific, layered, nested structure of our actual position in the cosmos, from the immediate interstellar neighborhood to the large-scale cosmic web. And the act of building that address, of pointing instruments in both directions perpendicular to our planetary disk, and measuring what is there, at every scale from the heliosphere to the edge of the observable universe, has been one of the most productive scientific programs in human history. Every major advance in cosmology over the past century has involved looking in or near the directions we call above and below our solar system. The discovery of dark matter in the Coma cluster above us, the first detailed maps of the cosmic web from the SDSS, concentrated near the northern galactic cap. The Hubble ultra-deep field below us, reaching back to the universe's first light. The Planck CMB all-sky map containing the anomalies aligned with our ecliptic plane. The directions above and below are not special because the universe is different there. They are special because they are the directions from which our galaxy's disk obscures the least. The clearest windows through which we see the universe as it is everywhere. This knowledge was built over the past century by an accumulating sequence of instruments and ideas and patient, careful observation. Hubble's measurement of the Andromeda distance, Zwicky's dark matter calculation in the Coma cluster, directly above us. The Voyager probes that sailed through the heliopause and into the interstellar medium that fills the space above and below the ecliptic plane. The Gaia satellite that mapped the three-dimensional structure of the local bubble with unprecedented precision. The JWST images that reach backward in time to the universe's first few 100 million years in the direction pointing below our solar system. The question, what is above and below our solar system, sounds simple. Child simple. Point at the sky and ask what is there. The answer is a structured, layered, historically contingent, scientifically hard-won map of everything from the gas immediately beyond our heliosphere to the most distant objects the universe allows us to observe. A map that is incomplete in its details, still being revised by every new survey and every new instrument, but coherent in its architecture and extraordinary in its extent. Above and below our solar system is the universe, all of it in both directions, with different features and different structures in different directions, all of it visible if you know where to look and how to look and why it matters that you look at all. The solar system is a small, flat, inclined disk moving through the galaxy on a 225 million year orbit, bobbing 200 light years above and below the galactic midplane on a 64 million year oscillation, embedded in a bubble carved by ancient supernova, currently passing through a wisp of warm interstellar gas, surrounded on its north ecliptic face by the richest nearby galaxy cluster, and on its south ecliptic face by the site of the deepest view of the observable universe. That is what is above and below. That is where we are. And knowing where we are, knowing the specific, layered, structured, historically contingent position we occupy in this universe, is one of the most profound achievements in the history of the species that has been pointing at the sky and asking questions since before it had language to ask them in. We are somewhere very specific. And now we know where. The knowledge feels different when you hold it whole rather than piece by piece. Not just the Virgo cluster above and the Fornax cluster below. Not just the local bubble and the galactic oscillation and the Oort cloud, but all of it simultaneously, nested inside each other like a set of Russian dolls, except that each shell is a different kind of structure, operating on a different scale, formed by different physics, connected to the next shell out in a way that is not nesting but interaction. The heliosphere pushes against the interstellar medium that fills the local fluff. The local fluff is embedded in the local bubble, whose shell concentrates the star-forming clouds that will produce the sun's future neighbors. The local bubble is embedded in the Milky Way's disk, whose tidal force drives the galactic oscillation that bobs the solar system up and down through different interstellar environments. The Milky Way is embedded in the local group, which is embedded in the Virgo supercluster, which is one of the structures that defines the local cosmic web. The local cosmic web is a specific region of the observable universe, itself a sample of the full universe whose extent may be infinite. Each shell is real. Each one has physical consequences for what happens inside it. The cosmic ray flux inside the heliosphere is affected by the heliosphere's interaction with the local interstellar medium. The local interstellar medium is shaped by the local bubble. The local bubble is shaped by the supernovae of the Scorpius-Centaurus-OB association. The oscillation through the galactic disk changes the cosmic environment on million-year timescales. The large-scale cosmic web determines the gravitational flows that govern the local group's motion. From where you are right now, sitting on the surface of a planet orbiting a star, embedded in all of this, the directions of above and below are specific, meaningful, and knowable. Above, through the local fluff, through the local bubble, out through the galactic disk perpendicular to its plane, toward the Virgo cluster and the northern cosmic web. Below, the same nested exit in the other direction, toward the Fornax cluster and the deepest views of the universe ever assembled. Every photon that ever arrived at the Hubble Space Telescope from the Hubble Ultra Deep Field passed through all of those nested structures on its way from a galaxy at the edge of the observable universe to a detector in orbit above Earth. It crossed 13 billion light-years of cosmic time. It passed through voids and filaments and the diffuse intergalactic medium. It entered the Milky Way from the direction of the south galactic pole. It traversed the local bubble. It passed through the local fluff and the heliosphere. It hit the mirror. In the direction below our solar system, pointing toward the Fornax region and the south galactic and ecliptic poles, every one of those photons traced the same path backward in time and space to the specific cosmic address from which the universe in that direction was observed. That is what is below our solar system. That is what is above it. There is a final thought worth sitting with, and it concerns not what we see, but how we see it. The human species has been on Earth for roughly 300,000 years. For the overwhelming majority of that time, the answer to the question, "What is above you?" was the sky, the dome of light and darkness that covers the world, the stars that appear at night and disappear at dawn. Something beautiful and mysterious and entirely beyond reach. In the past 100 years, less than 0.1% of our species' existence, we have answered the question completely. We know what is above. We know the specific structures, the specific distances, the specific cosmic history of the objects in both directions perpendicular to our planetary disk. We have mapped our cosmic neighborhood from the interstellar gas immediately surrounding our heliosphere to the galaxies at the edge of the observable universe. We have done this not through revelation or philosophy, but through the patient, methodical, cooperative work of science, building larger instruments, developing more precise methods, sharing data across institutions that command borders, building on each other's work across generations. The answer that science has assembled is more detailed, more structured, and more astonishing than anything that could have been imagined before the instruments existed to measure it. Above and below our solar system is, in both directions, the full depth and breadth and history of the observable universe. accessed most clearly because these are the directions where our own galaxy gets most out of the way. We are somewhere very specific. And now we know where.